Hello, good evening, and welcome. Did you know that as we drift through time, a simple mathematical curve drawn centuries ago by a man named Johannes Kepler still guides satellites and spacecraft across the star-filled abyss? That's right. The mystery of planetary motion, which for millennia was believed to follow perfect circles, is in fact governed by elongated shapes, ellipses, a discovery of such depth and beauty that it forever changed our relationship with the night sky. Our everyday intuition tells us that Earth and its neighboring planets circle the sun in smooth, constant, round paths. But the truth is far more subtle. A planet, in its cosmic ballet, never maintains the same speed. It accelerates and slows down in a dance that is perfectly choreographed. What exactly makes this choreography so precise? And why do these ancient laws remain the foundation of all modern space engineering? I invite you now into a gentle journey where we will uncover not only how the planets move, but why the elegance of Kepler's laws continues to captivate the minds of scientists and dreamers alike, revealing a secret about gravity that transcends time. But before we continue, I need your help. If you value this journey of knowledge and tranquility here at Cosmos for Rest, take a quiet moment to support the work. Subscribe so you won't miss future explorations, and share this story with someone who might appreciate a calm encounter with science. Your thoughtful support allows these reflections to continue. Now, settle in, close your eyes if you wish, and let science gently guide you. The starting point for our deeper reflection does not lie in distant galaxies, but in the patient gaze of a man named Johannes Kepler, who lived in the early 17th century. What makes his story and his laws so intriguing, even for us today, is that he refused to accept the geometric perfection that philosophy and nearly 2,000 years of tradition had imposed upon the heavens. Throughout recorded history, humanity believed that the motion of the skies, being divine, must unfold in the purest and most perfect form imaginable, the circle. This belief was a dogma, inherited from the cosmology of Ptolemy and Aristotle. Even Copernicus, who dared to remove Earth from the center and place the sun in its position, preserved the rigid circularity of the orbits because the idea of celestial perfection was simply too powerful to abandon. Kepler's journey, therefore, is one of scientific humility, in which he confronted that tradition not out of arrogance, but because he was compelled by the undeniable stubbornness of observational data. The treasure that guided Kepler came from his mentor, the astronomer Tycho Brahe, who left him an immense and meticulous archive of celestial observations, especially those detailing the motion of Mars. Tycho had devoted his life to recording the positions of the planets with a precision unmatched in his time, and those numbers became the ultimate judge of any theory. The mystery began because no matter how ingenious Kepler was in his calculations, trying to force Mars's orbit into a circle, even resorting to the desperate tactics of ancient astronomers by adding small auxiliary circles called epicycles, the theoretical prediction always failed. There was a discrepancy, a small but persistent error, of only 8 minutes of arc between what the circular model predicted and what Tycho had actually observed. Imagine that difference. 8 minutes of arc is like looking at a star and noticing that it is slightly displaced in the sky by the width of a strand of hair held at arm's length. For anyone else at the time, that discrepancy would have seemed insignificant, dismissible, easily attributed to instrumental error or minor imprecision. But Kepler knew the almost obsessive precision of Tycho Brahe. He understood that if the data were irrefutable, then the error was not in the observation, but in the very model of the universe itself. In that moment of frustration, caused by such a tiny failure, philosophical astronomy died and modern empirical science was born. It was no longer a matter of which geometric form was more beautiful or philosophically worthy of the heavens, but which geometric form actually described reality. After years of failed attempts, testing and discarding countless hypotheses, including the possibility that the orbit might be an oval shape, though not quite an ellipse, Kepler finally arrived at his first and most radical conclusion. Planetary motion does not follow circles, but ellipses. In his first law, the law of orbits, he declared that each planet moves in an elliptical orbit, with the sun positioned at one of the two foci of that ellipse. That simple statement carried the weight of 2 millennia of dismantled tradition. Think of an ellipse as a circle that has been gently stretched. It has 2 centers, or foci, instead of a single center. The sun occupies only one of those foci, leaving the other empty. This acceptance of the ellipse as cosmic truth is the true beginning of our journey and the foundation of all the intrigue. The ellipse immediately reveals why the distance between a planet and the Sun is constantly changing throughout the year. When Earth is closest to the Sun, it reaches the point called perihelion. When it is farthest away, it reaches aphelion. If the orbits were circles, that distance would always remain the same. The ellipse, rather than the circle, marks the moment when human knowledge stopped dictating how the universe ought to be and began accepting how it truly is. Yet, the enduring intrigue lies especially in the nature of what Kepler discovered. His laws were purely descriptive. He uncovered the how, the exact geometric pattern of motion, but he had no idea why the orbits took that shape. He speculated about a kind of magnetic force emanating from the Sun that swept the planets along their paths, an idea that turned out to be physically incorrect in detail. For him, the beauty of the ellipse reflected divine harmony, but the mechanism behind it remained hidden. He provided the coordinates of the stage and the choreography of the dance. The invisible dancer, the force pushing and pulling, remained unnamed. The simplicity and elegance of his law created the mathematical skeleton that awaited the flesh of physics, which would be supplied decades later by Isaac Newton. By accepting the ellipse instead of philosophical perfection, Kepler's work became the essential springboard for our modern and profound understanding of gravity. Kepler's journey teaches us a lesson in serenity and patience. He spent years of his life in tedious calculations, working with raw observations, searching for the hidden symmetry the universe had drawn. His persistence in resolving an error of only 8 minutes of arc stands as a testament to the idea that scientific truth hides in the most stubborn details, the ones most people would prefer to ignore. And it is precisely that attention to detail that invites us now to relax, to close our eyes, and to contemplate how deeply ordered the silent dance of worlds truly is. The first law gives us the setting, the shape of the orbit, and prepares us for an even greater revelation, that the Sun is not merely the center, but a focal point that shapes the very geometry of space around us, even before the word gravitational had fully taken conceptual form. Accepting the ellipse as universal truth was the first great step in deciphering the enduring mystery of planetary motion, showing us that cosmic order is elegant, but rarely obvious. If Kepler's first law gifted us the shape of the stage, the ellipse, his second law reveals the living rhythm of that motion, and it is here that the planetary ballet unfolds with particular beauty and mystery. In this quiet contemplation, we begin to perceive that a planet's speed is not a constant march around the Sun. It is, instead, a symphony that accelerates and slows in a rhythm both predictable and elegant. The intrigue here is not the shape, but the graceful variation of time itself. Kepler's second law, often called the law of areas, states that the imaginary line connecting a planet to the Sun sweeps out equal areas in space during equal intervals of time. To understand this gently, imagine a vast pointer, almost like the hand of a cosmic clock, stretching from the center of the Sun to the center of the Earth. As the Earth glides along its elliptical path, that pointer traces out an area in space. What the law tells us is that if we measure the area swept by that pointer over the course of 1 month, that area will be exactly the same no matter where along the ellipse that month occurred. The only way this can happen is if the planet's speed changes. When the Earth is closer to the Sun, at a point we call perihelion, the thread connecting it to the Sun is shorter, and the planet must move much faster to sweep out an area equal to the one traced when the thread is long. When it is farther away, at aphelion, this means that during one part of the year we are accelerating toward the Sun, driven by a growing attraction, and during another we are slowing as we move farther away, gaining a breadth of distance. This motion, though variable, is governed with absolute order and precision, and that is the planet's true rhythm. For us, living on Earth, this change in speed is far too subtle to feel in daily life, yet it is real and essential to understanding our place in the system. The second law was an even deeper rupture with the physics of its time than the ellipse itself. Ancient philosophy assumed that celestial motion, being perfect, must be uniform and constant. Through observation, Kepler introduced the idea of motion that varies yet remains perfectly ruled by mathematics, dictating the tempo of attraction. It was the first clear observational clue that a force was acting continuously upon the planet, regulating its speed according to its distance. He did not know what that force was. He speculated about magnetic influences or other subtle emanations. Yet his law provided an exact and elegant map of its effect. And this is the essence of the Keplerian intrigue. He mapped the effect without knowing the cause. The planet, in its routine, is constantly adjusting its pace to balance its energy. When the sun pulls more intensely at perihelion, it gains speed. When it drifts outward and the attraction weakens, it is allowed to slow and breathe. This law of variation gives life to our solar system and forms the mechanism behind modern space navigation. If we close our eyes and imagine a spacecraft traveling toward Jupiter, engineers must calculate its acceleration and deceleration with precision. They rely on this law of areas in what is known as a gravitational assist maneuver, or gravitational slingshot. The spacecraft approaches a massive planet, uses the speed gained during its approach, and is flung toward its next destination. The planet not only attracts it, but in its own orbital motion lends kinetic momentum to the probe, all in perfect obedience to the rule of equal areas. This shows that the laws Kepler uncovered centuries ago still function as the instruction manual for our exploration of the universe. The deeper scientific secret hidden within the law of areas is that it is, in truth, a geometric and elegant manifestation of the conservation of angular momentum, one of the most fundamental principles in all of physics. A planet's angular momentum, which measures its tendency to continue rotating or orbiting, must remain constant. When the planet moves closer to the Sun, reducing the radius of its path, it must increase its linear speed to compensate and preserve total angular momentum. Think of an ice skater spinning. When they pull their arms inward, reducing their radius, they spin faster to conserve angular momentum. The planet does the same. Kepler saw the geometry of this conservation long before Newton formalized the physical principle. For us, in this moment of calm reflection, the law of areas offers a gentle and profound metaphor for our own experience. It teaches us that our personal rhythm in life is variable, and that this variation is not chaotic, but ordered and necessary. There are moments like perihelion when we are drawn toward action, when energy rises and our pace quickens, and there are moments like aphelion when the pull feels more distant and our tempo softens, allowing us to slow, rest, and reflect. The value of our time, the area swept in our journey, remains constant and meaningful regardless of the speed of our steps. The universe values the consistency of the area traced, not the relentless uniformity of velocity. It is a lesson in cosmic balance, where acceleration and deceleration are essential components of a harmonious and sustainable path. As we close our eyes and allow our own rhythm to vary, we encounter the same subtle order that Kepler discovered in the motion of the worlds. The second law is the melody of time upon the stage of the ellipse, a melody that, because it describes rather than explains, still invites us to search for the deeper rhythm of nature. Its apparent simplicity, expressed as a direct observation about areas, conceals a principle of conservation that extends across all of physics, from the smallest scales to the grandest structures. The planet's fascinating routine, governed by the law of areas, shows us that order in the cosmos is not synonymous with monotony. It is a movement of breath and impulse, of attraction and release. And it is this choreography, traced with the precision of angular momentum, that ensures Earth always returns to its starting point at exactly the right time, year after year, sustaining the cycle of life and seasons. The enduring intrigue lies in the fact that Kepler glimpsed the tip of this vast iceberg of conservation simply by observing how a planet swept equal areas, proving that patient observation can unveil the deepest secrets of the universe. If the first two laws revealed the path and the individual rhythm of a planet, the third law, known as the Harmonic law, leads us into a deeper and more systemic level of understanding. It no longer focuses on a single planet, but establishes the rule of interdependence that connects the destiny, the time, and the distance of all bodies orbiting the Sun. Here we encounter the master architecture of the solar system, a silent mechanism that dictates the order of distances and durations, unveiling the profound harmony we seek in the universe. The third law states that the square of a planet's orbital period, that is, the time it takes to complete one full revolution around the Sun, is directly proportional to the cube of the semi-major axis of its orbit, which we may gently consider as half of the planet's average distance from the Sun. In contemplative terms, this law tells us that a planet's cycle of time is determined, with exponential precision, by its distance from the solar center. The farther away it is, the slower its cycle will be. Yet this relationship is extraordinarily powerful and exponential. The strength of the law lies in the exactness of this square and cube proportion. With each increase in distance, the time of the cycle grows disproportionately, following this precise mathematical rule. This proportion is not accidental. It is the mathematical fingerprint of gravity woven into the fabric of space. This law reveals that the solar system is not a chaotic collection of wandering bodies, but a perfectly scaled and interdependent architecture. It was the most elegant map of cosmic order humanity had discovered up to that time. By applying this simple relation, observation transforms into precise calculation. If we know Jupiter's average distance from the Sun, we can predict its orbital period. If we know how many years Saturn takes to circle the Sun, we can calculate its average distance. It is a powerful predictive mechanism that turns observation into certainty. Kepler's strategy in uncovering this law was guided by his search for a world harmony, believing that the ancient idea of the music of the spheres could be translated into exact and quantifiable mathematical proportions. He succeeded, but without knowing the true engine behind that music, which is why this law remains so compelling. What makes this law enduringly fascinating is its purely descriptive nature, devoid of physical explanation. Kepler knew the relationship existed, but he did not know why the square of the period should relate to the cube of the distance. It functioned with the precision of clockwork, yet the hidden gears, the force imposing that order, remained invisible. He saw the pattern governing weight and time, but not the force distributing them. That gap between how and why is the true source of intrigue. The third law was an extraordinarily accurate mathematical compass, but not the complete map. It pointed directly toward the necessity of a universal physical force, one that connected the Sun simultaneously to every planet and diminished predictably with increasing distance. It was precisely the elegance and exactness of this proportion that became one of the master keys for Isaac Newton. Decades later, when Newton formulated his law of universal gravitation, he realized that Kepler's third law emerged naturally as a necessary mathematical consequence of his theory. The deeper mechanism, the secret behind the harmony, was gravitational attraction. Kepler's discovery validated Newton's theory, providing the observational proof that gravity decreases with the square of the distance, the only way the harmonic law could mathematically hold true. Kepler's law was not replaced by gravity, it was explained and confirmed by it. And therein lies the historical and scientific beauty. One man perceived the pattern, the other revealed the engine that produced it. The beauty of this law also resides in its universality. It does not apply only to the Sun and its planets. It extends to any orbital system anywhere in the universe, from moons circling Jupiter to exoplanets orbiting distant stars. This law forms the heart of applied orbital mechanics and is the first calculation engineers perform when determining the trajectory of any object launched into space. Consider a low Earth orbit satellite, positioned close to our planet, completing a revolution in roughly 90 minutes. Now think of a geostationary satellite, placed much farther away so that it moves in sync with Earth's rotation, taking 24 hours to complete one orbit. The difference in orbital time is dictated precisely by the square and cube relationship Kepler uncovered, demonstrating the timelessness and applicability of his rule. In this moment of tranquility, the harmonic law offers us a vision of vast interconnection and order. As we close our eyes and meditate on the proportion of square and cube, we can imagine the grand scale, understanding that the majestic slowness of Neptune, which takes more than 164 Earth years to complete its orbit, is a direct mathematical consequence of its immense distance from the Sun. The third law teaches us that the solar system is a finely tuned mechanism. The harmony among the planets is not accidental, but the reflection of a singular physical law. It invites us to rest in the certainty that an underlying order exists, a graceful proportion governing cycles of time and distance on a cosmic scale. The precision of its terms, the use of square and cube, is not a mathematical coincidence. It is gravity's imprint upon space itself. The harmonic law is, in essence, the master key that opened the door to modern physics. It demonstrated that the order of the universe is not merely geometric, but deeply quantifiable. And that is why, even in an era of interplanetary travel, the elegance of Kepler's discovery continues to intrigue and astonish all who study it. Its surface simplicity conceals the profound complexity of gravitational attraction that governs everything. The deepest secret, and perhaps the most enduring mystery, surrounding Kepler's laws does not lie merely in the fact that he discovered the how without the why, but in the way their absolute precision becomes subtly fractured when confronted with the true complexity of the real universe. In their original form, the three laws possess unquestionable beauty, yet they hold a hidden truth. They are perfect approximations, the most elegant solution to an idealized scenario: a single planet orbiting an infinitely more massive sun, undisturbed by anything else. The most intriguing realization is that in the real cosmos, these laws have limits that only advanced celestial mechanics would later reveal. And it is precisely within the small cracks of these approximations that the deeper complexity of planetary motion continues to fascinate and guide us toward new discoveries. One of the greatest mysteries, which required centuries to fully understand and calculate with precision, is the concept of perturbations. Kepler offered us a two-body ballet, a planet and the sun. Yet the solar system is composed of 8 major planets, along with countless asteroids, moons, and other bodies, all exerting gravitational attraction upon one another. These mutual attractions, though minuscule and nearly imperceptible compared to the sun's dominant pull, create subtle disturbances that cause the real orbits of Jupiter, Saturn, or Earth to deviate slightly from their perfect Keplerian ellipses. Earth, for example, does not follow only the path dictated by the sun. It is also gently tugged by the immense mass of Jupiter. This additional pull causes Earth's ellipse to rotate slowly in space, or to change shape ever so slightly over tens of thousands of years. The enduring intrigue, therefore, lies in how Kepler's simplicity becomes the gateway to complexity. Modern scientists do not discard his laws. They use them as the first-order solution, the foundation upon which perturbations are calculated. The motion we truly observe in the sky is the sum of Kepler's perfect ellipse plus a series of small oscillations and deviations caused by the presence of all other celestial bodies. For centuries, mathematicians and astronomers wrestled with the profound question of stability. Despite all these pushes and pulls, would the solar system eventually return to a predictable equilibrium? Or is it inherently chaotic and destined one day to unravel? The beauty of Kepler's laws lies in their predictive power. When small discrepancies appear, they reveal the presence of something new, perhaps even something invisible. A classical and magnificent example of revelation through perturbation is the discovery of Neptune. In the early 19th century, astronomers noticed that Uranus did not follow the perfect ellipse predicted by Kepler's laws and Newton's gravity. The discrepancy was subtle, yet persistent, an error that could not be ignored. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that the only possible explanation for the perturbation in Uranus's orbit was the existence of an 8th planet, still unseen, whose gravity was pulling Uranus away from its ideal Keplerian path. Neptune was discovered in 1846, precisely where calculations based on the failure of Uranus's ellipse had predicted. The secret hidden within Kepler's laws was the location of an entire world, invisible until then. Yet an even deeper mystery emerged in the orbit of Mercury. Astronomers observed that Mercury's perihelion, the point where it is closest to the Sun, advanced slightly faster with each orbit than predicted, even after accounting for all known perturbations caused by Venus, Earth, and Jupiter. This tiny anomaly, amounting to only 43 arcseconds per century, remained unresolved for decades. It was not solved by discovering another planet, but by the necessity of an entirely new physical theory: Albert Einstein's general theory of relativity in the early 20th century. Einstein's theory revealed that the sun's mass does not merely exert a force, as Newton had described, but actually warps the very fabric of space-time around it, as though the sun were sinking into a vast cosmic mattress. Mercury, being the closest planet to the sun, orbits in a region where the curvature of space-time is more pronounced. Kepler's laws, grounded in Euclidean geometry and Newton's instantaneous attraction, represent the low-speed, weak gravity approximation of this deeper reality. Mercury's anomaly was a whisper from the universe, suggesting that space and time themselves are flexible. The mystery unveiled by this Keplerian deviation was the need for an entirely new physics. This reveals that Kepler's laws are not the final chapter, but the most compelling invitation to explore deeper dimensions of physical reality. Their enduring intrigue lies in their ability to serve as both foundation and subtle clue to discoveries that surpass them. These small deviations and perturbations offer us a serene reminder, as we close our eyes, that mathematical perfection is only a reference point. The real universe is a place of evolving complexity. Kepler's ellipse provides the piece of order, while the slight oscillations in planetary orbits remind us that everything in the cosmos is interconnected. Nothing is truly isolated. Jupiter's pull on Earth and the curvature of space-time caused by the Sun are subtle layers that add depth and mystery to the system Kepler mapped. The true measure of the enduring intrigue of Kepler's laws lies in their extraordinary capacity to connect and influence fields far beyond 17th century observational astronomy. They are not museum artifacts of scientific history, but living tools that shape our technology and our understanding of physics on scales Kepler could never have imagined. The most immediate and profound connection is with Isaac Newton's law of universal gravitation. Kepler's laws served as the observational proof Newton required. Without the geometric precision of Kepler's ellipses and the exact harmony between period and distance, Newton could not have formulated his fundamental law. Kepler provided the mathematical map, the description of how the universe moves, while Newton supplied the physical engine, the explanation of why. Newton demonstrated that Kepler's three laws were the direct and inevitable mathematical consequences of his premise. The gravitational force between two bodies is proportional to their masses and inversely proportional to the square of the distance between them. This unification marked the first great triumph of theoretical physics, revealing that the same laws governing a simple apple falling to Earth also govern Jupiter orbiting the Sun. The intrigue persists because Kepler's laws remain the most tangible and beautiful bridge between pure geometry and the physics of force. They compel us to see that mathematics is not merely a descriptive tool, but the deepest expression of physical reality, a principle that became the foundation of all science that followed. The impact of Kepler's laws extends into space engineering and navigation in ways that have shaped our modern world. Every aspect of orbital mechanics that enables satellites to fly, interplanetary probes to travel, and even the precise positioning of the International Space Station is built upon the Keplerian foundation. To calculate an orbit, engineers begin with the Keplerian solution, assuming the simple dance between two bodies, and only afterward do they add the complexities of perturbations, such as the Moon's attraction, Earth's equatorial bulge, and atmospheric drag. The law of areas is used to calculate the precise launch windows for missions to Mars, ensuring that a spacecraft arrives at the exact point in the planet's orbit at the exact moment the planet itself will be there. This precision is not improvised. It is a direct consequence of understanding how areas are swept in equal times and how velocity varies along an elliptical path. Even when we speak of complex interplanetary flights involving multiple gravitational assists, the central calculations depend upon Kepler's harmonic law, the so-called Hohmann transfer orbits, the most fuel-efficient elliptical paths used to move spacecraft from one orbit to another, are direct applications of the proportional relationship between the square of the orbital period and the cube of the semi-major axis. The harmonic law allows engineers to determine with remarkable accuracy how long it will take a satellite to complete its orbit at a given altitude. This predictive power forms the backbone of our communication networks and global positioning systems. Consider how deeply we depend on GPS precision in daily life. That precision begins with Kepler's mathematics applied to the orbital motion of satellites. The contemporary lived reality of his laws is quietly woven into the technological fabric of our everyday existence. Beyond engineering, Kepler's laws transformed extragalactic astronomy and the search for exoplanets, connecting the motion of planets in our solar system to the farthest reaches of the universe. The third law, relating orbital period to distance, is used in reverse to weigh distant stellar systems. By observing the motion of a star and measuring the orbital period of a companion star or planet around it, scientists use the harmonic relationship to calculate the mass of the central star. This simple yet powerful technique is essential for characterizing stars, black holes, and distant planetary systems. Without the Keplerian framework, determining the mass of most celestial objects in orbital motion would be dramatically more difficult. Likewise, the detection of exoplanets through the radial velocity method depends on measuring the tiny wobble a planet induces in its host star. That wobble is an elliptical motion around a shared center of mass. Kepler's mathematics deciphers this motion, allowing scientists to infer the invisible planet's mass and orbital period. Laws discovered by studying Mars's orbit in the early 17th century are now used to map systems thousands of light years away. This universality is what makes them timeless and profoundly intriguing. They function not only in our solar system, but anywhere Newtonian gravity applies, demonstrating that cosmic order is governed by unified principles. The influence of Kepler's laws also reaches into the conceptual structure of science itself. They represent the triumph of empirical evidence over philosophical authority. They mark the transition from Aristotle's universe, where what was rational or beautiful dictated reality, to the universe of modern science, where observation and mathematics are sovereign. Accepting the ellipse over the circle was an act of intellectual courage that opened the path to the scientific method we use today. The intrigue of these laws lies not only in what they reveal about motion, but in what they represent about the power of evidence. They demonstrate that truth about the cosmos is not written in ancient texts, but encoded in precise observations and the mathematics that interprets them. This intimate connection to the foundation of physics invites us once more to close our eyes and find serenity in the interconnectedness of knowledge. What began as Kepler's frustration with the orbit of Mars became the key to unlocking the masses of distant galaxies and guiding spacecraft with extraordinary precision to other worlds. These laws show us that knowledge is cumulative, that each discovery, no matter how old, becomes the necessary step toward the next revelation. The ellipse of Kepler, the rhythm of the law of areas, and the harmony of the harmonic law are the quiet pillars supporting our spacefaring era. Their presence reminds us that even amid the turbulence of discovery, there exists a stable mathematical foundation upon which we can build our understanding of the universe. The intrigue awakened by Kepler's laws in our understanding of planetary motion is inseparable from their profound resonance in the history of human culture and consciousness. They represent far more than a shift in mathematical formulas. They symbolize a fundamental and irreversible change in humanity's position within the cosmos. Consider for a moment the psychological comfort offered by the ancient universe. For millennia, Ptolemy's geocentric system, with Earth motionless at the center of everything, anchored humanity in a place of unquestioned importance. We were the focal point of creation, the central stage upon which all celestial drama unfolded, granting our existence a sense of purpose and centrality beyond doubt. The initial transition to Copernicus's heliocentric model, placing the sun at the center, was the first shock, a destabilization of our cosmic geography. But the truly profound cultural revolution, the one that removed us from the pedestal of perfection, came only with the acceptance of Kepler's ellipses. The ellipse, with its subtle asymmetry, its gently imperfect shape, and its sun positioned off-center at one focus, delivered the final blow to human cosmic arrogance. It removed us from a universe of static perfection, the metaphysical and divine circle, symbol of absoluteness, and placed us within a universe of dynamics and less obvious geometry. The ellipse was physical. It was the direct and inevitable consequence of forces acting in space, not of philosophical design. Humanity was compelled to accept that the heavens were not a realm of ideal forms, but a domain governed by precise mathematics, accessible through observation and calculation. This radical acceptance marked the rise of reason and empiricism over blind authority, becoming a defining pillar of modern science. Kepler's work, alongside Galileo's telescopic observations, did more than correct astronomical tables. It initiated the Age of Enlightenment and paved the way for the scientific revolution. This transformation influenced not only science, but the very method by which society began to pursue knowledge. Through evidence, experimentation, mathematical analysis, and the rejection of dogma that could not withstand factual scrutiny. The intrigue lies in how a seemingly minor deviation in geometric form, the ellipse instead of the circle, produced such seismic consequences for our intellectual and cultural self-understanding. Tycho Brahe's precision and Kepler's courage in following the data became the enduring model for all subsequent scientific inquiry. Reality prevails over speculation. This shift in perspective resonated deeply within philosophy, art, and even architecture in the centuries that followed. The ancient idea of the music of the spheres, a Pythagorean belief that planets produced mystical harmony as they moved in perfect circles, had long served as a poetic metaphor for cosmic order. Kepler himself sought to quantify this harmony in his third law. He did not abandon the idea of harmony. He translated it. What had once been mystical music became exact mathematical proportion. The harmony was no longer symbolic, it was measurable. The universe began to be seen as a vast and predictable clock, operating according to immutable laws. This mechanistic vision influenced thinkers such as René Descartes and Gottfried Wilhelm Leibniz, fostering the belief that the cosmos could be fully mapped and understood by the human mind, provided it was equipped with the proper mathematics. Confidence in humanity's ability to uncover the deepest secrets of nature and to use that knowledge to shape the world was a direct legacy of Kepler's precision. The ellipse gave us certainty that order was not magical, but mathematical. This was one of the greatest intellectual liberations in history. The human mind shifted from passive observer to active decoder of the universe's underlying code. That conceptual transformation continues to echo in our persistent search for patterns and laws. Historically, the practical impact on navigation was equally transformative, altering the course of civilizations and enabling the era of global exploration. Before Kepler and Newton, long-distance navigation relied heavily on estimation, empirical knowledge of winds and currents, and often imprecise maps. It was an act of faith as much as calculation. Kepler's laws, by providing the first truly accurate description of planetary motion, enabled the creation of far more precise astronomical tables. Consider the problem of longitude. To determine east-west position at sea, one must know the exact local time and the exact time at a reference point. Determining local time required knowing the precise position of celestial bodies, especially the moon. The ability to predict the moon's position far into the future, with the precision demanded by elliptical orbits and the law of areas, formed the foundation for determining longitude at sea. Accurate mapping of the planet, expansion of trade, establishment of global empires, and colonization of distant continents were, in significant part, indirect consequences of Kepler's work. Knowledge of the heavens became essential for mastering the oceans. His ellipse did not merely reform astronomy, it made possible the age of exploration and globalization that shaped the modern world. It is remarkable to consider that a calculation concerning the orbit of Mars became a key to global cartography, and yet the enduring intrigue remains in how Kepler's laws, even after being surpassed by Einstein's general relativity, continue to serve as our starting point. When we revisit them today, they offer a serene and essential perspective on our true scale and significance. The ellipse reminds us that we are not the absolute center, but one planet among many, following an ordered and inevitable path, a grain of sand in a cosmic dance. This cosmic humility, born from Kepler's precise mathematics, underlies our modern search for exoplanets and for life beyond Earth. To accept that our orbit is governed by the same forces that rule every other celestial body is a mark of scientific maturity. As we close our eyes and contemplate the ellipse, we accept our place in the cosmic ballet, not as its focal point, but as participants in a greater order. Kepler's greatest contribution to humanity was to provide mathematical proof that even as a peripheral body in an imperfect orbit, our motion is governed perfectly by universal law. This understanding of order and position allows us to relax, knowing that we belong to a larger and harmonious mechanism. The discovery that the cosmos follows rules, and that the human mind can decode them with mathematical precision, is Kepler's most profound gift to the human spirit. It is this certainty of order, even amid our spatial insignificance, that gives his work its deepest beauty and its most enduring intrigue. The future of Kepler's laws does not lie in their replacement, for they remain a perfectly functional and elegantly concise description of motion. Their future resides in their continued integration and expansion into scenarios far beyond the boundaries of our solar system. The enduring intrigue of this subject is, paradoxically, its universality and resilience. The ability of a discovery born in the heat of the scientific revolution to survive and flourish in the era of advanced astrophysics. What Kepler uncovered in the orbit of Mars is now applied and tested in realms of complexity and scale that challenge our imagination and invite us to dream. The first and most crucial field of future application, one that invites us to close our eyes and imagine new worlds, is exoplanet astrophysics. Consider the harmonic law, the rule that links orbital time and distance. Today, it is the essential starting point for calculating any newly discovered world orbiting a distant star. When astronomers measure the time an exoplanet takes to transit across its star, or detect the subtle dimming and wobble caused by what is known as the radial velocity method, they rely on Kepler's cube and square proportion to determine that planet's orbital distance and, crucially, to estimate the mass of the star it orbits. This elegant connection between period and distance allows astrophysicists to construct models of distant star systems and to identify where the so-called habitable zone may lie, that delicate region where liquid water could theoretically exist on a planet's surface. The future search for extraterrestrial life ultimately depends on the precision and reliability of Keplerian calculation. A rule formulated in the 17th century stands as the foundation for some of the most cutting-edge science of the 21st. The intrigue lies in the simplicity of the formula. It allows us to probe the vastness of the cosmos using the order discovered within our own small system as the key to decoding others. Another frontier lies in advanced space navigation, particularly in what is known as multi-body orbital mechanics, the challenging problem involving 3 or more gravitational bodies. Kepler's laws describe perfectly the motion within a 2-body system, but the universe is far more populated. The future of space exploration will involve extended missions in complex gravitational environments, such as the Lagrange points, where the gravitational forces of the Sun and Earth balance in delicate equilibrium. At first glance, these trajectories may appear chaotic. Yet they are mapped by using Keplerian solutions as highly accurate initial approximations, later refined with sophisticated perturbation calculations and, when necessary, corrections from general relativity. The development of interplanetary highways, or transport networks that exploit subtle gravitational interactions to move spacecraft using minimal fuel, depends upon understanding how Kepler's ellipses are distorted and interconnected under the influence of additional bodies. The Keplerian orbit is the main road. The future lies in mastering the subtle paths and deviations that make long-term exploration sustainable and efficient, transforming perturbation from mystery into engineering tool. Beyond practical application, the future of this theme extends into theoretical physics itself. Because Kepler's laws emerge as direct consequences of Newtonian gravity, they represent the classical limit of Einstein's general relativity. In regions where gravity is relatively weak, such as most of our solar system, the predictions of Einstein, Newton, and by extension Kepler, align almost perfectly. Kepler's law marks the mathematical boundary where relativistic physics simplifies into classical description. This creates a powerful conceptual role for the future. Any attempt to formulate a quantum theory of gravity, one that unifies relativity with quantum mechanics, must, under conditions of low velocity and weak gravitational fields, reduce back to Kepler's ellipses. His laws serve as a test of coherence for any deeper framework. The persistence of the ellipse, even in the laboratories of the most advanced theoretical physics, stands as testimony to its fundamental truth and to nature's preference for elegant simplicity. In the realm of data science and complex systems modeling, Kepler's laws offer a paradigm of refined simplicity within dynamic systems. The ability to reduce the intricate motion of a planet to 3 concise equations continues to inspire researchers across disciplines, from climatology and ecology to economics, to search for underlying patterns capable of describing apparent complexity with comparable elegance. The elliptical form and harmonic proportion extend metaphorically into our search for order in systems that seem chaotic, yet reveal predictability under the correct mathematical lens. Kepler's capacity to extract order from a mountain of observational data remains a model for modern artificial intelligence and data science. His patience, his insistence on respecting data over assumption, is a lesson that continues to guide scientific inquiry today. In this quiet moment of reflection, the future of Kepler's laws invites us to close our eyes and consider the resilience of knowledge. A discovery born from painstaking calculations of Mars's orbit not only survived the rise of relativity and supercomputers, it became the foundation for exploring planetary systems light years away. The future of the cosmos is charted with ancient geometry. The elegance of the ellipse offers us a stable anchor of order amid the infinite mystery of space. It reminds us that while our tools evolve and our theories deepen, the fundamental patterns discovered through patient observation endure. The curve traced centuries ago continues to guide humanity outward, quietly, precisely, and with unwavering reliability. We have reached the end of our gentle journey, and I invite you now to take a slow, deep breath, to feel the weight of your body settling into rest, and to carry with you the greatest secret revealed by Kepler's laws. The final intrigue, the one that transcends mathematics and physics, is that the elegance of the universe is not hidden in distant realms. It is encoded in the very geometry of our own motion, in the dance we perform every single day. When Kepler corrected a tiny error of only 8 minutes of arc, he did more than replace the circle with the ellipse. He replaced a universe of unquestioned dogma with a universe of verifiable patterns, a cosmos where patient observation becomes the key to revelation. Accepting imperfection in form, the ellipse instead of the circle, was the ultimate act of scientific humility, and it continues to guide our search for understanding. The ellipse, he discovered, invites us into profound cosmic humility. It reminds us that our path is not perfectly centered or symmetrical, yet it is undeniably ordered. Reflect on the law of areas, the subtle rhythm of the cosmos. It teaches that variation in speed is not chaos. There are moments of perihelion, when life's pull feels intense and we are propelled forward with urgency. There are moments of aphelion, when we drift outward, slowing down, gaining distance, and finding space to reflect. The beauty lies in knowing that the value of our time, the area traced by our effort, remains constant, regardless of how fast or slow we travel. Order does not demand uniformity. It requires balance, a breathing harmony between impulse and rest. The harmonic law in turn reveals our deep interconnection. It shows that our cycle of time and our distance are governed by a universal proportion, linking Earth to all its neighbors. We are not alone in the dance. The majestic slowness of Neptune and the swift orbit of Mercury are equally necessary within the same mathematical harmony. Each body's rhythm is a direct consequence of its place within the system, all synchronized by the invisible force of gravity. The enduring intrigue of Kepler's laws is that they serve as a bridge. They connect philosophical speculation to the physics of force. They were the treasure map that guided Isaac Newton toward the discovery of universal gravitation. They remain the geometric foundation that allows our GPS satellites to function with precision and enables scientists to probe worlds light years away in search of life. The ellipse is our legacy, a curve shaped by gravity that teaches us to seek order in detail and to accept that beauty often resides in subtle deviation rather than perfect symmetry. The predictability of motion, even when it is not circular, is where true elegance resides. As you close your eyes now, feel the reassurance of that order. The universe is not chaotic, but vast and governed by elegant proportions that the human mind can patiently decipher. Earth's motion is predictable. Its speed is calculable. Its path is defined by solar attraction. This certainty of order is the gift Kepler left us, the peace that comes from knowing we are part of a greater choreography. Remain in that serenity, aware that this cosmic order is always present, always guiding, always inviting you to rest within its quiet mathematical beauty. If this reflection has brought you a sense of calm and wonder, consider continuing this journey with Cosmos for Rest. Subscribing allows you to return whenever you wish to explore science in a way that steadies the mind and softens the night. You may also share this experience with someone who could use a moment of quiet connection with the universe. Your support gently sustains these contemplative explorations. For now, let the elegance of the cosmos carry you into peaceful rest.